Okay, well, it's 2 after, so I think I should get started. So today we'll talk a little bit about what's up in the nighttime sky. The nighttime sky is kind of short these days, but that's good. We've been waiting for that. And then we're going to talk about how observations with the James Webb Space Telescope are really taking our old ideas of how galaxies form in the very early universe and completely turning them upside down. So first, let's start up with what's up this month. The moon was new yesterday. So over the next couple of weeks, it will be growing in size. And tomorrow, if you look for the crescent moon just above Jupiter, this is a diagram showing it to the west, northwest after sunset. Sunset tomorrow is about 8:34 p.m. So if you look around 9 p.m., you ought to be able to see again Jupiter way down on the horizon and the crescent moon just above it. The next full moon is on June 11th, and it's called the strawberry moon in honor of all the strawberries that are out in June. As far as the planets are concerned, Mercury is hidden, it's lined up with the sun, and you can't see it. Venus is very bright, rises almost due east at the very beginning of dawn, so you have to get up at 4 o'clock in the morning. Mars is high in the west in the evening, and so here's a diagram that shows where the moon will be later on this weekend. Here's the moon on May 31st, and Mars will be just above that. But this is looking halfway up towards the west. We just saw where Jupiter was. Saturn rises in the east before dawn, so it is close to Venus, but it's much, much fainter. So you have to either look for the planets right around sunset or after sunset, and you could see Mars and Jupiter, or if you get up really early in the morning, you can see Venus and Saturn. Okay, so now let's talk a little bit about distant galaxies. And what I'm going to try to explain is what we mean by distant galaxies, why we think how they would be different from galaxies today, and how the James Webb Space Telescope, because of its design, is really allowing us to learn things we had no way of learning before. So here's an image taken with the Hubble Space Telescope of a bunch of objects that you can see outlined by these diamonds. And here are some images of them above. And these are what we would call candidates for being distant galaxies. The fact is, Hubble really was able to find really distant galaxies only by the handful. And the reason for that is because of its design. Hubble is only a 2.4-meter diameter mirror, whereas JWST is a 6.5-meter mirror, which means that JWST has a lot more light gathering power. It can collect a lot more photons because its area is 6 times greater. JWST is also equipped to observe in the near to mid-infrared in what you might see with your nighttime vision goggles, whereas HST was designed principally to observe in the optical to ultraviolet. And we'll see that distant galaxies should be red, so observing them in the infrared is better. So as I said, Hubble only found a few dozen galaxies with the very highest, what we call redshifts, meaning that we are observing them as they would have appeared within 600 million years after the Big Bang. Whereas already, even though it's only been operating for a few years, JWST has already found more than 1,000. So here's a little blinking image that shows you the same field on the sky, but one image, the one that looks a little greener or orangier, was taken with Hubble, and the crisper, sharper one was taken with JWST. Remember that these spikes that you see are artifacts of the instrument itself because there's a really bright star here and it scatters some of the lights and you end up with these what we call diffraction spikes. So JWST, as I said before, is a bigger mirror, so it collects more photons and therefore you can see fainter objects. And JWST observes infrared light where Hubble observes mainly visible light. So let's remember what I mean by infrared light. Here is what you could see with an infrared enhanced camera observing at night. And here's what you would see with a standard night vision camera. And you can see you can detect objects that are much, much fainter, mainly because they emit more light in the infrared, and so they're easier to see with a device that's specifically designed to detect infrared radiation, which has a longer wavelength than what our eyes can detect. So let's think about what we mean by understanding distant galaxies. So remember that when we look out into the universe further and further away, the light that we detect has to have traveled longer and longer from when it was emitted to when we receive it. So looking out in distance is actually looking back in time. We also think about our Big Bang model of cosmology and the expansion of the universe. This event that we call the Big Bang occurred about 13.7 billion years ago. The Milky Way, which is our galaxy, formed about 13.2 billion years ago. So say 500 to 600,000 million years after the Big Bang. But remember that the solar system and the sun formed only 4.5 billion years ago. So in fact, we would say, astronomers would say that the solar system formed in a mature universe. And what we're interested in is studying the very early universe. Distant galaxies, because they're so far away, are going to appear small and very faint. And additionally, because of the expansion of the universe as predicted by what's called Hubble's law, the light from those galaxies will appear to us to be redshifted. That is, everything about their light is shifted to longer wavelengths, so they will appear redder than a nearby galaxy that would otherwise look exactly the same. And here are some of the examples of galaxies that we've actually now been able to detect with JWST, and they kind of look like normal galaxies. Well, some of them look a little weird, and they're all small and faint. So here's our picture of cosmology. Here's the modern universe today. Here's time on the horizontal axis. Here's the modern universe. And if we look back 13.7, 13.8 billion years, we end up with the event that we call the Big Bang. The part of the history of the universe that we're interested in talking about today is way back, looking this way, 13.6 billion years or so, but looking this way, 200 million years or so after the Big Bang. This is the era that we call cosmic dawn, when the first stars, maybe the first galaxies, maybe the first black holes formed, heated up the universe and ionized all of the neutral gas which was present back in what we call the dark ages before there were any stars. And this is what we're interested. These very early times when the first stars and galaxies formed, somewhere in the range between 200 and 600 million years after the Big Bang. So again, looking out is looking back. Light travels at a finite speed, 186,000 miles a second. When we view a distant galaxy, we see light that left that galaxy billions of years ago. So if we can observe the distant universe, we can observe the young universe. We're observing the universe at an earlier age in its history than we can observe locally. And when we talk about a galaxy being redshifted, we're talking about its spectrum being redshifted. And what I mean by that is if we take up the light from a galaxy and we break it up into its individual wavelengths. If a nearby spiral galaxy shows a spectrum that looks like this, going from short wavelength to long wavelength, it will have this pattern of dark lines in it due to atoms and molecules and ions in the atmospheres of all the stars, the billions and billions of stars that are contained in the galaxy. If I were to observe that same galaxy more redshifted, then the spectrum would look similarly in the sense that it would have the pattern of these lines, but the lines would all be shifted towards the red, which you can think of as being longer wavelength or redder color. And if we observe a really, really distant galaxy, the same pattern of lines appears, but they're all shifted even more towards the red. So that this line is this line, and this line is this line, and this line is this line, etc. That's what we mean by redshifted. The whole spectrum is shifted to longer wavelengths. Longer wavelengths are red. So the spectral lines have the same pattern, which tells us about their chemical composition and temperature and density, but they're all shifted from the wavelengths we would expect to see in a nearby galaxy. Now, not all galaxies have the same color to start with. And so here's a montage of what we call Hubble's galaxy classification scheme. And I mean Hubble here, not Hubble the Space Telescope, but Edwin Hubble, the guy for whom the Hubble Space Telescope is named. One of the many things that Hubble contributed to our understanding of the universe is he took many, many galaxies, looked at them, and said, let's make a morphological sequence, a sequence of principally their shape, going from elliptical galaxies to spiral galaxies. He also noticed that some spiral galaxies have a bar in the center and some don't. That's going to prove to be a second order effect, and we're not going to worry about it. But we are going to notice that the elliptical galaxies have different degrees of ellipticity or squashing. The spiral galaxies have a nucleus and then spiral arms, and some of them are tightly wound and some of them are loosely wound. But another important fact is that elliptical galaxies appear redder, and spiral galaxies, as you go along the spiral sequence, appear bluer. Now, these are all nearby galaxies, and so we have to understand that if you take any of these galaxies and observe them far away, their light will all be shifted into the red, and so the blue ones will look red even though they're not, and the red ones will look even redder than they should. So there are other things that we need to understand about the difference between the ellipticals and spirals. Ellipticals are generally red even in the nearby universe, discounting the effect of the redshift. They have little cool or cold gas. They are not currently forming stars. So in fact, we say they're red and dead. And they also, if we look at their stars are in random orbits around the center. There's no disk. They're three-dimensional objects. Spiral galaxies, on the other hand, have lots of cold and cool gas, and they're currently forming stars. Where in this galaxy, all the stars are old. In a spiral galaxy, some of the stars are old, but others are forming, they're young, and they're forming even now. But not all spiral galaxies are forming stars at the same rate. In fact, we can break up spiral galaxies into two categories: normal star-forming spiral galaxies and star-bursting spiral galaxies, which are actually forming stars at a very high rate, but only for a short period of time. And they're also fundamentally different from ellipticals, because the stars and gas orbit in a disk plane, a thin disk. it turns out there's another difference that we need to keep in mind that will turn out to be important. Elliptical galaxies are like urban dwellers, and spiral galaxies are kind of like suburban to rural dwellers. In other words, elliptical galaxies like to come in aggregations of many, many thousands of galaxies, what we call clusters of galaxies, and the spiral galaxies avoid the centers of the clusters of galaxies. So there's some effect that seems to be at play that has to do with the galaxy's environment. Okay, so we have our distant galaxies are expected to be small and faint, and their light will be redshifted. As I said before, the blue galaxies, when viewed in the distant universe, will appear red, and the red galaxies will appear even redder than they would have if we viewed them close up. So we're looking for red objects, small objects, and faint objects. Another thing about the universe, and this relates also to environment, is that on large scales, the universe is expanding because it got kicked out and everything started moving away from everything else when the event called the Big Bang took place. But locally, in other words, in the environment of a galaxy close to it, gravity causes masses to attract other masses. And so locally, galaxies can actually pull on one another and form small groups of galaxies or small aggregates of 3 or 4 or 5 galaxies, which can actually continue to interact by gravity. That's important because we observe that galaxies can interact gravitationally by the gravitational force with other galaxies. Those interactions, as we'll see momentarily, can cause galaxies to become active. And it can also even cause 2 galaxies that are close together to be attracted by their gravity, merge together. And whereas before you had 2 smaller galaxies, you end up with one bigger one. So um, let's take a look at what we mean by activity in galaxies, some of which is certainly related to where a galaxy is and whether or not it has companions. So there are different kinds of events, ongoing activity in galaxies. One are the formation of tidal tails, collisions between galaxies, and mergers of galaxies that can occur when you have 2 galaxies interacting by their gravitational forces. Here's a tidal tail. Here's a case where we think there were actually 2 galaxies that got so close together, they're in the process of merging to form a bigger one. Then sometimes we have galaxies that we call starbursts. And here's an image of a famous galaxy, M82. And what you're seeing in the red color is material that has been heated up because this galaxy is making stars at a very, very high rate. And then we can also have what we call active galactic nuclei, where in the center of a galaxy, we could have a point-like source, a star-like source, that shows evidence of hot, fast-moving gas clouds, high-energy photons, which we believe is the accretion of material around a supermassive black hole located at the center of the galaxy. So here's what I mean by a tide and then a merger. So what you see in this simulation, and we'll take a look at this twice, is we start out with 2 disk galaxies, kind of spiral-like galaxies. But because they're close together, they feel the gravitational pull of the other galaxy, and the center of the galaxy has more pull than as we go further out. So this causes material to be pulled from one galaxy into the other one. The galaxy's shapes are distorted, And sometimes it also causes gas and stars to fall into the center of the galaxy. And in this extreme example, you take two galaxies, you start out with two galaxies, but over the course of probably 1 billion years, the two galaxies become one. And so gravitational interactions can cause activities in galaxies, shifting material around, feeding supermassive black holes, and causing the galaxy, as we'll see, to turn out to be brighter than it would be normally. So here's an example. We're going to take a look at an example. Here's our starbursting galaxy that I showed you before called M82. Here's a nice spiral galaxy, which we believe looks very similar to the Milky Way. And notice this other little galaxy down here, which isn't very prominent at all. These galaxies are all at roughly the same distance from us. They're nearby. That's why you can see so much detail in them. But we've understood that if you look at these galaxies, in starlight, you see this picture. But if you look at a radio image tracing the cool gas in the system, you can see that the galaxies are actually connected by gas. Presumably, our idea would be that they are undergoing gravitational tidal interactions, and some material is being pulled out of this galaxy onto this one, maybe being pulled out of this galaxy onto this one, and you also end up with this tail here. So can we simulate that? Well, the answer is yes. So this is kind of a very simple simulation, but watch the yellow galaxy on the bottom and the green galaxy on the top kind of exchange places. And we end up with this tail that we saw in the radio image. So again, we are able to actually understand this because we can make these simulations, which are based on the laws of physics. And we see that galaxies can interact. Material can go from one galaxy to the other. Material can go from the outer part of a galaxy to the inner part of the galaxy. And this stimulates changes in the appearance of the galaxy and also can cause them to form more stars than they had been in the past. And that's what we end up with. We think this galaxy M82 is a starburst galaxy that is making stars, that it's converting gas into stars at a rate about 10 times greater than what is happening in the Milky Way. We don't think this can happen forever. It's been caused by this gravitational interaction, and we call this, therefore, a starburst. The other interesting kind of galaxies, which also could be affected if you had material moving from one galaxy to another or from the outer part of a galaxy to the inner part, is this idea of what we call an active galactic nucleus. Here are a couple of real images. Here's the artist's conception. We have a supermassive black hole that might have a mass 1 billion times the mass of the sun, located at the center of a galaxy. So here you can see the galaxy, but you can also see this point-like star, very bright nucleus at the center. Because the galaxy has some rotation usually in it, you end up with what we call an accretion disk of material around, close in, but very, very close in to the supermassive black hole. And here's an example of that. In this case, the galaxy, this is only the central nucleus of the galaxy. The galaxy is huge on this scale. And sometimes we get jets of radiation emanating from the nucleus, which show up at radio wavelengths. What we understand is that material is being accreted towards the supermassive black hole. It gets heated up and it outshines the rest of the galaxy. So now, when I talk about activity in galaxies, I'm talking about any of these things: the tidal phenomena, the mergers, the starburst, the active galactic nucleus. Sometimes we see that the activity is evident via morphology, the shape of the galaxy. Sometimes we see it because when we look at the spectrum of the galaxy, we see spectral lines that imply that the gas and the ions are very, very, very hot, much hotter than you would see in a star, for example. And sometimes a galaxy can both be a starburst and a supermassive black hole. And we don't really know what might cause and what might be the cause and what might be the effect. The importance of all of this in bringing this up is that when you have a starburst or when you have the accretion onto the supermassive black hole, the object, the galaxy, the galaxy that hosts the starburst or the galaxy that hosts the active galactic nucleus becomes much brighter than it would be otherwise. So if we're going to take a sample of galaxies in the distant universe, we're not looking at average galaxies. We're looking at active ones, the brightest ones, and we have to keep that in mind in interpreting the population. So, galaxies can interact, causing them to be brighter and more active, even causing them to merge, which would cause them to grow over time. When we look at galaxies at optical or in optical wavelengths, especially, we see starlight, and different stars evolve at different rates, mostly depending on their mass. Young stars are luminous and blue. Old stars are red. And so if we see blue stars, we know we're looking at star formation that has just happened within the last 500 million or a billion years. And then we can also ask ourselves, will galaxies change color depending upon whether their stars are old or young? And the answer to that is yes. And that may happen. Things may change over the course of lifetime of galaxies over the 13.7 billion years of the history of the universe. And we call that the star formation history. And there are different possibilities. One possibility, which could explain many elliptical galaxies, is that all of the gas in the galaxy was converted into stars all at once in the first billion years of the history of the universe. The galaxy is red and dead. It's not forming any more stars now because it used up all the gas. Another idea is that and this might work for spiral galaxies. We believe that star formation in spiral galaxies occurred and peaked within the first billion or so years after the Big Bang, and then it kind of slowed down, but it continues to be ongoing. Another idea might be that star formation proceeds all at constant rate, but that doesn't seem to happen. That seems to be too easy. Star formation doesn't proceed in a galaxy at the same rate throughout its history, probably because galaxies interact with other galaxies, as we've just been talking about. That's why environment is very important. And in some instances, like in the case of M82, Messier 82, the starbursting galaxy, we think that over the last billion years or so, out of the 13.7 billion years, the galaxy has received a new supply of gas and has undergone a starburst. So we have to keep all this in mind, that the universe isn't a simple place. It's dynamic. Galaxies are crashing into each other, or they're having some little tango together as they interact gravitationally, but they don't get too close. The universe, things are changing all the time. And so if we want to understand the distant universe, we have to keep all in mind all of the things that could be changing over the course of history. So again, back to what we're interested in is this 400 million years or so after the Big Bang. So we have the Big Bang and we have today. And we think that the first stars formed, what we call cosmic dawn, occurred 200 to 400 million years after the Big Bang. Hubble was able to tell us that there was another event, which we might call cosmic high noon, which was the period when most of the stars in the universe were formed. The sun was actually formed after that, long after that. So remember that the sun was formed in a mature universe, and the sun, relative to lots of other stars, formed after the average star. Okay, so we now understand that distant galaxies are small, faint, and red, that we're going to preferentially see the ones that are active, that ones that have young massive stars are going to be extra luminous and blue and have spectral lines that tell us that there are young massive stars in them. And very massive galaxies, and ones that are gravitationally lensed, which I'm not going to talk about, will be easier to detect than others. And David has his hand up. David, you'll have to unmute yourself.
So I have a question. You said that galaxies can obtain more gas. Where do they get it from? Isn't there a finite amount of gas in the universe?
They can get it from another galaxy let's say you have two galaxies. One is an elliptical, it's red and dead, it doesn't have any gas. But nearby, there's a spiral galaxy that hasn't turned all of its gas into stars yet. It hasn't gotten around to using up its fuel. But they come close together, and some of the gas from that spiral galaxy can get dumped onto the elliptical galaxy, and suddenly the elliptical galaxy can form stars again. That's my simple picture. It's not that simple. In fact, in between the galaxies, there is gas that has not formed stars. And so that is also a supply of additional fuel. But again, it's not as simple as you'd like it to be, because the universe is a very dynamic place. So that is one of the reasons why I'm not going to be able to answer all the questions about what's going on, because it proves out to be extremely complicated. Galaxies are affected by their environment. They can be affected gravitationally, um, between the two galaxies that are visible. But remember, there's all this gas out there that doesn't show up to optical telescopes at all, that can also allow a galaxy that wasn't forming stars for 5 or 6 billion years to suddenly form stars. In the early universe, there was a lot more gas than there is today floating around waiting to be made into stars. Okay, there's one more thing that one more complication. We're looking for small, faint red objects. But we have to remember that if we have a galaxy that is very, very far away, it could appear redder for various reasons. If we have two galaxies, one being very red. One reason is because the galaxy has no young massive stars. Young massive stars are blue. If the galaxy has no young massive stars, it's going to look red. Another thing that we haven't really talked about, but I have talked about in other times, is that if a galaxy contains a lot of dust, and dust usually is made out of things like carbon and silicates, and it has dust in between the stars in the interstellar medium, the dust absorbs and scatters blue light more than red light, and therefore the galaxy looks redder because of the dust. Here are some examples of that. Here's a Hubble image. Here's a JWST image of the same object, and you can see all this dust. that doesn't really show up in this image, although you can see some of the artifacts of it as being dark, meaning the absence of light, because the light isn't getting through because of the dust. And here's a composite image. And then there's a third reason why a distant galaxy might appear red, and that's because of the redshift. But the bottom line is we're going to look for objects that are small and faint and red. And then we have to figure out which ones are really distant galaxies, which ones are closer but are red because they have no massive young stars, or which ones might be closer and look red because they contain a lot of dust. Because there are three possibilities for why a galaxy appears red. Okay, so now not just looking at the color, but if we can look at the galaxy with a spectrograph or a spectroscope rather than a microscope, and we can take its light and break it up into its individual colors, and then measure the flux in the galaxy from blue light to red light, from short wavelength to long wavelength. Galaxies have different spectra. In particular, if you look at an elliptical galaxy that's far away, it shows the spectrum characteristic of the atmospheres of all the stars in the galaxy, but it doesn't have any gas. So you don't see, you see no evidence of gas. If you look at a star forming or an active galaxy with an accreting supermassive black hole, it will have the underlying shape. See, there's an underlying shape that's similar to this, but then you see these increase of flux at very discrete wavelengths, which are due to the bright emission lines indicative of hot gas that has been heated up either by star formation or the supermassive black holes. So with a camera, you can just look at the different colors of the galaxy. With a spectrograph, you can take a much more detailed look at how the light varies as a function of wavelength, and you can find these spectral lines. Now, let us say that I have an elliptical galaxy, kind of something that looks like this. And if I observe it in the nearby universe, the spectrum looks like this, okay? It rises and then it kind of falls off, and it has those dark lines that appeared in the other one, which are where the flux drops out because of the atmosphere of all the stars that we're looking at. This is the spectrum of an elliptical galaxy in the nearby universe. As we move to further and further objects at larger and larger distances, that entire spectrum is shifted towards the red. So here's a nearby galaxy, here's one that's pretty far away, and here's one that's even further away. And what we've done with Hubble is gone out and observed the galaxy in a bunch of different filters. You put a filter in the camera, and it measures the flux in this wavelength range, in this wavelength range, in this wavelength range, in this wavelength range, and in this wavelength range. And we would expect, therefore, the galaxy to show up brightest in these short wavelength filters if it is nearby, and it won't show up much in those filters if it is far away. Instead, the galaxy will peak at longer wavelengths and will appear red. The problem, of course, is I'm showing you a red and dead galaxy. Not all galaxies are red and dead, so when we look at galaxies that have star formation and possible activity, this gets much more complicated. But the basic idea of trying to find distant galaxies is we start out taking a set of images. And so here's a JWST image. We put different filters in front of the camera, and we measure the amount of the brightness of the galaxy in those different filters. And if the galaxy is a truly distant object, it won't look bright in the short wavelength filters. It will look bright in the long wavelength filters. And so if we look with a single JWST image, you might see in that image 10,000 galaxies. You need to narrow down what you think are the distant ones by looking at all the different filters. So this just shows you 3 examples of objects which were picked out by JWST to appear to be potentially, based on how bright they were in the different filters, could be distant galaxies. What we do then is that is what we call a photometric survey. So photometric, you're trying to measure the brightness of the galaxy in different images taken with different filters. And you're able to look at 10,000 galaxies, and you find that 20 of them look to be very distant objects because they don't really show up in the shortest wavelength filter, but they do show up in the other filters. Then you can, and that's observationally cheap, because for every image you take, you get 10,000 galaxies to search through to find 20 that look really good. But it doesn't take you that long to do that. If you want to get a spectrum, you have to take the light and break it up into small little bins of small wavelength elements. To get a spectrum takes much more time in terms of observations. It might take 1 hour to get all of your images, but it might take 10 hours to get, with a ground-based telescope, a single spectrum. Even with HST, it takes much longer to get a spectrum of an individual object. So you don't want to look at spectra of 10,000 objects. You only want to look at spectra of 20 objects, and you want them all to be distant. That's the problem. So JWST has a spectrometer. Here are some examples of some of the objects it has found. Looking back 11.3 billion years, 12.6, 13.0, 13.1 billion years ago, the spectrometer allows us to test not just the image tells us the galaxy is red. The spectrum allows us to test, why is the galaxy red? Is it because all the stars are red? The galaxy has a lot of dust. It's very distant. And of course, what we want is to find the ones that are distant, which may or may not also be red or blue or dusty. So here's an example of one of these extremely high redshift objects, which we look at. Here's the image itself. When we use a camera and a telescope, there are always artifacts. So we model what we're seeing and subtract off to make sure that we're not picking up some cosmic ray or some other artifact. Here's an object which barely shows up. It shows up in these filters. It doesn't really show up in these short wavelength filters. These are all JWST filters in the near infrared. This is the spectrum of the object. And here are how it was observed with the different filters to get these images. It was decided that it looked like a good candidate, and you can see in the actual spectrum itself, it doesn't show up in the short wavelength filters. These are in microns. But there are, in fact, spectral lines that show up when you take the spectrum. So again, JWST is now trying to identify individual objects by looking for what we call these spectral dropouts. When the camera images show nothing, but then the object shows up when you go to the longer wavelengths, and then we go back and we take spectra. Now, I've made this sound much easier than it is. The images are all taken with different filters, which have different sensitivities and also resolutions. Some of the images are blurrier than others. So all of those things have to be accounted for. So if it sounds really easy, it's not. But here are some examples of spectra that were identified from the images, and then when they've gone out and they've actually taken the spectra, you see there are these emission lines from star-forming active galaxies, and as we look at the lines, they become increasingly red-shifted, and that tells us how far away the object is. Okay, so here's another example of a particular galaxy which we are viewing 13.1 billion years in the past. In other words, about 600 million years after the Big Bang. Notice it has spectral lines which tells us that it has oxygen, hydrogen, neon, and in other cases we can see other spectral lines of things like carbon and silicon. And so all putting this together, this is now informing us about what these early galaxies are like. So let's understand what we saw before JWST. There were very few direct observations. We understood that galaxies form within dark matter halos. That is still the current understanding. We understand that the rate of star formation has something to do with the growth of dark matter halos and the inflow of gas. We understood before that galaxies should grow over time, that in the past they would be smaller and less organized, less structured. We believed that spiral structure would develop much later. We thought that the reionization of the universe was caused by low mass star forming galaxies. And we also thought we didn't understand that there should be supermassive black holes in early galaxies, at least rather than being billions of solar masses, we expected them to be only millions of solar masses, because we don't know how those black holes grow anyway, but we assume that they grow over time. So what JWST has done, which surprised us, and again, these are some JWST images of extremely distant objects. These few were formed in the first 200 to 300 million years after the Big Bang. And it has found more than 100 times, a number density of these sources, more than 100 times greater than were predicted based on what we had observed with Hubble. Many of them have unusual properties. Maybe this looks like an interacting pair even. We don't understand those unusual properties. Some of them they are resolved. They're not point sources. They're not stars, but they're very, very compact, much, much smaller than the Milky Way. So we found some new kinds of objects that we really didn't expect to see. First of all, I said before, we thought all galaxies should be small. But in fact, JWST is revealing the presence of a very large number of very massive red galaxies. How could these galaxies become that big that fast? No way not in any way if they are forming stars the way stars in the nearby universe are being formed, at least at the same efficiency. We also see that they're extremely red, too red to just be explained by starlight. They have to contain a lot of dust. Some of them are completely invisible to Hubble. They show up in JWST, but they're completely invisible to Hubble. So here are some examples. Um, they are very dusty. They're invisible at optical wavelengths, but they're forming stars and they have these emission lines. They're forming stars furiously and extremely efficiently. And so the way these galaxies convert gas into stars is very different from anything that happens in the nearby universe. So that's a problem that has astronomers scratching their heads. We also, another confusing thing is our understanding of the way heavy elements, and what I mean by that are carbon, nitrogen, oxygen, all the stuff that we're made of. Our idea is that that has been built up, those elements have been built up by stellar evolution and supernovae over the course of the last 13.7 billion years. But some of these galaxies already have carbon and they have much too much nitrogen, which again is telling us that the way these early galaxies took gas and formed stars is very different from the process which is taking place in the universe today. And this is something we just don't understand. It's unexpected. Maybe what we're seeing is that lots and lots of supermassive stars formed that lived for very, very short periods of time. Collisions and tides caused gas to become very dense and very hot on very short time scales. But honestly, we don't know the answer to this. So we're back to the drawing board as to what the first stars are like and how they form and how they live. At the other end of the scale, we have the big red monsters. JWST has also discovered things called little red dots. And they are extremely red objects, and they're extremely small. They may be the size of only maybe 100 times the size of the solar system, and yet they're giving off huge amounts of radiation that we can detect. The two competing ideas are that the red color might arise from gas and dust in the accretion disk around a supermassive black hole. The problem with that is we don't know how to form the supermassive black hole. It may also be that these are regions of this extremely efficient star formation within more massive galaxies, but you can't see the rest of the galaxies. Or maybe it's both. But the bottom line is we don't really understand what these are. We don't know whether it's black holes or whether it's star formation or whether it's both, and we don't have any idea of how this can be going on. They have very unusual spectra. So here's one of these. It's called by this weird name. It appears to be a bright galaxy with a black hole superimposed on it, so that we end up with a spectrum that looks like this. So these are model galaxies, and this is what we actually see. It appears to be an extremely compact energetic source of a supermassive black hole inside a relatively low mass star forming galaxy. It's only one object. It's perhaps one of the only ones that has a really good spectrum at this point. So the question is, are all little red dots like this one? Or is this just only one object and we were lucky enough that this one seems to have a supermassive black hole? Then there's another category of galaxies which are discovered. JWST did some very early observations that were made available to everybody. And one team called the Sears team found a whole bunch of linearly shaped galaxies that they dubbed bananas, but they could also be called breadsticks or cigars. And these objects do not appear in the local universe at all. Um, they seem to be very common in the images that were analyzed by this particular team. Um, but we don't understand what they're like because we don't see them close to us. So again, we don't really know. What are these things? How did they form? These are bigger than the little red dots, but not as massive as the big red monsters. Then this one is just a really interesting object that popped up um, just a couple of days ago. It is the highest redshift that has been confirmed at this point. Again, it's a dropout. These are the different filters going from short wavelength in the infrared to longer wavelength in the infrared. Clearly, it shows up and then it doesn't show up, so it's a dropout because the spectrum falls off when you get to the shortest wavelengths. It's invisible at short wavelengths. We believe that we are seeing this about 280 million years after the Big Bang. And in fact, it was identified by looking at the different images, but then they've gone out with JWST and gotten a spectrum. And sure enough, it has this dropout. This is a galaxy observed at a redshift of 14.4, which means we're observing it when the universe was 280 million years old. Again, one object, we keep pushing further and further out, but this is how it's done. This is an interesting one because it shows no sign of a supermassive black hole, as opposed to that last one that I showed you. It shows evidence for carbon, nitrogen, and oxygen, and it looks like it's a burst. So are they supermassive black holes or are they star-bursting galaxies? So the bottom line is what JWST has revealed so far is that there are lots and lots of these distant galaxies, many, many more than we expected to find at these redshifts. There are lots of early massive galaxies that are well formed. Some of them have bars or spiral arms. Others appear to have these linear structures. This really wasn't expected. We thought we'd see early galaxies being small, clumpy, and irregular, and we don't understand how massive galaxies could form so early. There are galaxies that are forming stars furiously, and some of them already have carbon, nitrogen, and oxygen. We don't understand where the dust comes from. We don't understand a process of star formation that can generate so many stars with so much mass so quickly. It's not like what happens in the universe today. And then there are lots of galaxies, even low mass ones like the last one that I showed you, with supermassive black holes of masses a billion solar masses. They already exist and we can observe them. And we don't really understand how supermassive black holes can form so early. And that begs the question of which came first, the galaxy or the supermassive black hole? Do you have to have a supermassive black hole and then a galaxy forms around it? Or do you have to have a galaxy and then within that, a supermassive black hole form? We don't know. So in other words, JWST has completely overturned our simple ideas of how galaxies and stars formed in the early universe, which were based on our experience with Hubble of observing the universe at a billion years or later. But it turns out the early universe is really interesting, really confusing, really complicated, and JWST promises much more to come. So that's where we are today, and I'll stop and take any questions. Yeah, Anne, you have a question.
Well, it's almost more of an observation. My whole graduate work at Cornell was using vibrational spectroscopy. I did a little bit more Raman than I did infrared, but I can't tell you how this takes me back because it's just fascinating that an IR spectrometer is on the Hubble. And it is such a useful piece of equipment for identifying all kinds of things. So I just wanted to tell you how excited I was to see spectra that I really understood. This is a side of me that all the rest of the people don't know about is vibrational spectroscopy. It's really cool that what you're able to do.
Yeah, I think this also this idea of looking at high redshift galaxies is really the fundamental reason why JWST is JWST, and why it had not just the camera but the spectrograph. It's used for many other things too, but it was really designed in this way to be able to diagnose what's happening in these distant galaxies. And we had an idea, we had ideas of what was happening. We were wrong. Elena.
Well, this is really stretching my brain, and I'm going to have to go back and view this again after, the recording is posted. I'm used to looking on Mars using spectra to identify minerals, but taking that leap of using spectra to identify distance and time is an enormous stretch. And then
Yeah.
trying to grasp the redshift of a particular spectrum that moves, but that the same colors are displayed on that band.
Right. And that's why it's really complicated to do this diagnostic. When we take that one image with JWST or Hubble, and you detect in that image thousands of galaxies, most of them are in the foreground. They're forming stars, they have active galactic nuclei, or they don't, but they're in the foreground, they're not as redshifted. But we have to try and pick out of the thousands of galaxies the 10 or 20 that are really far away. But then in order to interpret them, we have to add in this redshift dimension. We have to remind ourselves that nearby we can see average galaxies, average mass, average brightness. Looking far away, we only see the brightest light bulbs. The brightest light bulbs are the ones that are active. And so we're not seeing an average population. We're really seeing an extreme population. But we have a tendency nearby to focus on understanding the average galaxy. And so we come up with models of how gas is converted into stars, and then stars shine and undergo nucleosynthesis and form the heavy elements. And we kind of know, we have a pretty good understanding of that in the Milky Way. And we'd like to think that it's not that different in other galaxies, because if it's too different in other galaxies, we have to go do a lot more theory, where it's back to the drawing board. We don't understand what's going on. But what we've really learned with JWST is that the early universe is a really weird place. And it's clear that there are processes of forming black holes, of forming stars, of forming galaxies that occurred then that aren't happening now. I think that's really exciting, but what it means is that our simple pictures don't work in this epoch of very high redshift. And so what's funny is in preparing this talk, which I also gave a slightly different version last week to our Cornell Friends of Astronomy. Sorry, Alan, I know you were there on that one. I was looking at the most recent papers on JWST, and what's really interesting is they come up, oh, we found a little red dot and it's got to be a supermassive black hole. Somebody else comes up, oh, we found a little red dot and it has no evidence of a supermassive black hole. And we're still working in the individual galaxies not having enough yet of a population where then you can try and look for secondary factors, like whether there are companion objects around or not. But it's why JWST is an amazing telescope, and why it does not appear to be on NASA's chopping block like some others. But anyway, I hope you've gotten the message that it's a pretty cool telescope. Alan.
How common do we believe that starbursts are among the spirals? Is it more like 1 in 1,000 or 1% or?
No, it's probably a few percent. And again, they come in different gradations. But nearby, a starburst probably is a few percent of spiral galaxies nearby, has a star formation rate that's 5 to 10 times that of the Milky Way. But for some of these early things, we're talking about hundreds of times greater.
Are the really early ones very bright? I mean, I hadn't kind of realized that, like, you spoke about this category of active galaxies. Are they, just kind of typical in brightness among the active galaxies?
No, they're at the extreme example. And they're among the extreme starbursts, the extreme actively accreting supermassive black holes. But that is in part because you're going to see those are going to be the first ones you discover, because they are the brightest light bulbs.
Yes.
And so what Hubble is doing, what JWST is doing, in fact, is they continue to observe a few fields over and over and over and over again. In part because then you could look for things that pop up or disappear, which are objects that are changing or moving, but also so that you can continuously add together all the images that you've taken, and that allows you to see fainter and fainter objects. So, we're already thinking of the next telescope, which we hope will be, even bigger, but I wouldn't count on that anytime soon. And again, JWST has a 10-year lifetime. That's what it's spec'd for. It could last longer than that. Hubble has lasted much longer than its specification. And we're not there yet. We still have a long way to go. So we hope to find more of these objects. I only peripherally mentioned, sometimes a foreground galaxy can actually cause a background galaxy to appear brighter and bigger in a phenomenon called gravitational lensing. And when you have gravitational lensing, the background object doesn't have to be active. It just has to be lucky enough to have another galaxy in front of it or close to in front of it. And therefore, gravitationally lensed objects don't have this extra luminosity bias, and they can be normal galaxies. But you have to be lucky enough to find them, and they're pretty rare. But again, as people continue to observe with Hubble, all the data becomes public after a short period of time. The people who propose to get the data have access to it for a fixed period of time, and then it becomes public. People are doing things with images that weren't intended to be done with them. And so over time, with Hubble, we've learned much more from analyzing archived Hubble data than was observed with the first set of images, with the first purpose of a Hubble image, because people keep developing smarter galaxy identification algorithms, smarter ways of guessing which ones are further away. And so there's a lot more to be done, but we have a lot more to do because we really don't understand what's happening. But the early universe, the first couple of 100 million years, was a really weird place. And there's a lot of work on the theory side to do because nobody worried about having you're not supposed to have supermassive black holes at these distances in this epoch, but they're there. So where do they come from? How do you form one? No one has any idea. Well, I'm sure some of my colleagues have ideas, but that's because astronomers have ideas that may or may not be true, right? Anyway, so I hope I've convinced you, if nothing else, that yes, and spectroscopy is awesome. And that JWST is just bringing all sorts of things to this field that are fascinating, surprising, unexpected, but also to other fields. And so I may have to talk sometime about other fields that I don't know anything about. And I guess that brings us to the next thing. Our next meeting is June 24th at 7 p.m. And then I agreed to do that one, and then I'm going to take 2 months off. But I'm going to Italy tomorrow, and while I'm there, I will ponder what to talk about on June 24th. I assure you I will be enjoying myself. Okay? Thanks
you.
for coming,
Thank you,
everybody.
and have a good trip.
I'm
Thank
going to
you,
do my
thank
best.
you.
Okay. Bye-bye, everybody.
Bye.
Goodbye, good trip.